Getting started in machine vision. Today we're going to talk about cameras, different types of cameras, different things to consider when selecting a camera, and how to select the correct resolution for your specific application. We're also going to talk about lensing, the types of lenses, what you need to consider when selecting a lens, and then how to select the correct focal length. So focusing on cameras, how do we know what the best camera is to choose for our application? There are optical considerations, there's area scan versus line scan, there's different camera functionalities we have to think about, and then we'll talk about some useful formulas to help you pick the correct resolution. Optical considerations we need to think about when selecting a machine vision camera. There's usually a number of trade-offs when designing the imaging system and choosing a camera. For the sensor size and pixel size, there are so many different sensor sizes, but what's the difference? In the early days, there was only a few, a quarter, a third, a half, 2/3, one. Today, there are over 3 dozen. And that's because varying the pixel size and sensor size expands the possibilities for imaging. So the trade-offs between light gathering capacity, field of view, and resolution, they're all considered with different sensors. Larger sensors collect more light and can help you capture better quality images, but they have disadvantages too. And they usually need a larger and more expensive lens. For pixel size and resolution, smaller pixels provide higher resolution for a given sensor size, but image quality can be degraded due to poorer light conditions and noise, and then smaller pixels also require higher resolution lenses. So the lens is not really the limiting factor, but they tend to be more expensive. Spec resolution appropriately, so don't overspec it and use the largest size pixels that you can. For the focal length, there are often multiple options when choosing the appropriate focal length. A good rule of thumb is to not get too close to your object. Field of views that are too large relative to a lens's working distance place excessive demands on the design of the optics and can decrease the system performance. We usually recommend that a lens be chosen so that the working distance is roughly 2 to 4 times as long as the desired field of view is wide. That's just to maximize the performance while minimizing the cost and complexity. The depth of field depends on essentially 2 things, the magnification and the aperture size. Larger depth of field and higher resolution are mutually exclusive, and you can't have both. So this is because maximizing the resolution and depth of field require the lens aperture to move in the opposite direction. So you can increase your depth of field by stepping down the lens, so a smaller aperture, but you will lose light and resolution. So we'll talk about that a little bit more. We'll talk about each one of these topics as the presentation goes, but that's kind of the rough breakdown of each one. Throughout the presentation, we're going to talk about a few fundamental parameters. So I'll go through the definition of each one so we're all on the same page. The first one is the field of view, which is the viewable area of the object under inspection. So if we ask you for the field of view of your camera and you just give us the size of your sample, that doesn't really help us. If you're inspecting the whole sample, the field of view is going to be a little bit larger than the size of your sample to account for some tolerance and positioning. If we're only looking at a small portion of your sample, we need to know what size that portion is. So the field view is not the size of your sample, it's the size of the area that we're looking. The working distance is the distance from the front of the lens to the sample. It can change based on certain lenses that you choose, or some lenses have a fixed working distance. We'll get to that later on in the presentation as well. The resolution is the minimum feature size of the object that can be distinguished by the imaging system. So the resolution of your camera, the smallest defect you can see, things along those lines. And the depth of field is the maximum object depth that can be maintained entirely in focus. So if you have a sample that's got varying heights, a larger depth of field, all of your sample will be in focus. A shorter depth of field, maybe only the bottom will be in focus, but the top is out of focus, or vice versa. The sensor size, the size of the camera sensor, every camera will have a sensor in it and they will vary in size depending on how many pixels there are and how large the pixels are. Usually the sensor size is specified in a horizontal dimension. We also can calculate the magnification of the lens, which is just the ratio between the sensor size and the field of view. So types of cameras, there are 2 kinds. There's area scan and line scan. Area scan is great. It can be taken for stationary objects and objects in motion. It captures everything in one frame, in one snapshot. It's determined by the resolution of your camera, so a kind of standard resolution is 480 by 640. 2 megapixels, 1200 by 1600 are kind of close to those numbers. and it can get larger. Kind of up to around 25 megapixel cameras are pretty available, but that's about as high as it goes within a smaller, more affordable cost. Versus line scan captures the images differently. Instead of capturing the whole frame in one like area scan, it captures one line at a time as the object is moving below the camera. I like to describe it as a loaf of bread. Consider every line is a slice of bread. If you put all the slices together, you get the loaf. This is the same thing. If you put all the lines together, you get your image. The benefit of line scan is there's a few. You can get really high resolution images because you only have one line of 8,000. The more lines you have, the higher resolution image you have, versus getting that same size image with an area scan. You're always going to be limited to the resolution of your camera. The other benefit is they can fit in small spaces. I've installed a line scan camera in between a conveyor where we needed to look at the bottom of the sample, and there was about 2 inches between conveyors that the sample moved over. We had a line scan camera looking up from the bottom, so we were able to inspect the bottom of the sample without having to flip it over, even though there's only a 2-inch gap. Downside is your object has to be moving. If it's not moving, you're just looking at one line image, and that's not going to get anybody any data. The difference between area scan and line scan in terms of resolution, here these pictures will look the same. If you look at them, you wouldn't say like one's significantly better than the other, but as we zoom in on the fine details, the area scan provides a lot less information than the 75 megapixel line scan camera. So depending on what we're inspecting for, this might be sufficient, but if we're trying to get these fine details, we're going to need a higher resolution line scan. So with line scan camera, we're able to get up to a 75 megapixel image. For the rest of the presentation, I'm going to be talking only about area scan cameras. Line scan cameras are, there's a lot of information that we can't tackle all of it in one webinar, so we're just going to focus on area scan from here on out. So in area scan cameras, there are different camera sensors that you can have, especially for monochrome cameras. There's the CCD sensor and the CMOS sensor. The CMOS sensor is definitely going to be more common in machine vision. It offers higher dynamic range and lower cost. It does have a little bit more noise than a CCD sensor, but it is a lower cost and has a faster frame rate. It's definitely getting closer to the quality of a CCD sensor, but not as great for low light applications for more things like astronomy and life science and stuff. But for machine vision industry, most of the sensors you come across are going to be a CMOS sensor. The sensor is made up of pixels that will vary in size. So the size of the pixels and the number of pixels will determine the resolution of your camera. And the way a sensor works is when light is shown exposed, when the sensor is exposed to light, the light captured is converted to the image with all the mechanisms within the camera. So that's kind of what the sensor is doing, is essentially creating our image. Color cameras also have a sensor, and they have different structure a little bit. So a single sensor color camera, it captures the amount of red, green, and blue light present in each pixel by placing a filter on top of the monochrome sensor. And then each pixel, it calculates the red, green, and blue values, combines them together to get a color image. There is also multi-sensor color cameras where essentially the light comes in, it hits a prism. The prism directs each wavelength of light in a different direction, and then there's a sensor there interpreting that wavelength for the color image. So the difference between these two, a single sensor camera will have false colors for images with high spatial frequency, and then the 3 CCD cameras will be captured correctly. Realistically, most of the inspections, especially if you're just looking for kind of presence absence of a label, there's lots of space, a single sensor camera, which is the most common, is going to be sufficient. If you're really looking at fine, not a lot of space, really specific colors, you might want to consider a 3 CCD sensor camera, but more often than not, a single sensor camera will probably be just fine for you. Cameras also have peak wavelengths. So a monochrome camera will have 1 peak wavelength, and this will vary for each camera in color and monochrome. So make sure if you're curious to what it is, look it up in your specs. This is a situation where if there's enough light and we have kind of excess light, this really isn't going to matter because our visible range is, 405 to, 700, 800. This is kind of IR range, but your red, green, and blue are all going to be around 80% or above. So we're still getting a large amount of light in the visible range that we don't really need to consider this. But if we're in a situation where we're really limited on light, we have a little bit, we just need a little bit more, and our application allows it, with this camera, it might be worth it to pick a green light that would, the sensor can respond to 100% of that green light instead of just 80% of a red light. So once again, not always going to come up or always going to be an issue, but sometimes it can be just the right amount of light to help our application be a little bit more reliable. For color cameras, each wavelength is going to have their own peak response, peak wavelength that it responds to, and that's again just a spec in the camera you can look up. Within area scan cameras, there are also different types of shutters. There's a rolling shutter and a global shutter. A rolling shutter essentially takes the idea of a line scan camera. The picture is captured by scanning across the scene rapidly, line by line. This has to be used on stationary targets, and I have a video in the next slide kind of showing why that is. The benefit to it is it does cost less than a global shutter. For a global shutter, the entire frame is captured at the same time, and it can be moved on using targets. Most of your machine vision cameras are probably global shutter, but rolling shutter is very common too, so just make sure you're picking the right type of shutter for your application if it's stationary or moving, and then considering the cost there as well. So here's a reason why we can't use a rolling shutter in a moving object. As the propeller moves around and that line goes down the image, the propeller looks warped. It doesn't look like it's straight, it looks like something's wrong. And then when our next image comes around, it's in a different spot. The propeller looks completely different than it did in the last image. So if we were trying to set this up on a machine vision line, every image would look different than the last one, which is very, very complicated to build a machine vision program when every image is slightly different than the last one. Back to area scan sensors. Your sensor size will come in certain formats. It'll say, 1-inch sensor, 2-inch sensor, they're 2/3 inch, etc. And that's measured in the horizontal direction, 11, 9, 8. It's important to know what the sensor size in your camera is for a lot of the calculations that we have later on, and very important for lensing. So this will come up a little bit more later, but this is kind of typically how the sensor sizes are broken down. When considering the pixel size, the common pixels are between 3 micron to 10 micron. Larger pixels are able to take in more light and in general have a higher charge saturation capacity and a little bit less noise. There's pretty much what you need to take away from this slide is use larger pixels whenever possible. You'll have lower noise and just a better resolution, better response. There are also different camera interfaces, and all of these have different trade-offs. If you're looking for speed only, you're going to want to go with the camera link. They're the fastest. If you have a lot of different cameras that are all looking at the same inspection you need to set up, then Gigi would be your best because it's easiest for multi-cameras. It also has the longest cable if you need to be far away from your actual computer. But if you're just looking for something that's really easy, your camera's not that, or your line's not that fast, etc., USB 3.0 is the best for plug and play, which we consider as automatic configuration without worrying about settings and drivers. Hot plugging is when you can just add or remove a device to a computer while it's running. So that's kind of the difference between these three. Really, when you're trying to think about your camera interface, you got to consider the bandwidth of your application, how long the cable needs to be, what the cost you're willing to spend is, and then the complexity of your application. So now we've kind of talked about all of the factors when choosing what kind of camera you want. Do you want line scan, area scan? Do you want global or rolling shutter? What sensor size are you getting? And then what interface do you want? But now we need to figure out what resolution of the camera we actually need now that we've kind of narrowed it down. So there are two ways to think about this. The first way accounts for motion. So if you want to calculate your NP, which is your number of pixels spanning the field of view, which is essentially your required camera resolution, you multiply the blur, which the blur is essentially how many pixels you allow to have blur. The rule of thumb is 1 or less, unless you do sub-pixel processing. Some cameras offer that, or some programs. But the good rule of thumb is to just do 1 or less. a lot of times we'll multiply it by 0.9 just to be safe, but 1 works well as well. So you multiply the blur by the field of view, and then you divide it by the speed of the part going below and the exposure time. The downside for accounting for motion in this formula is a lot of times we have 2 unknowns and 1 equation. We don't know the resolution, and a lot of times we don't know the required exposure. So we can't actually solve this formula with 2 unknowns and 1 formula. And when that happens, we go to this no motion factor to figure out what our best resolution is, and then we can go and calculate our required exposure time. So to go through the without considering motion and just trying to get the best image with the right resolving power, we have to think about what size defect we have, or what size part of our image we want to see, and how many pixels do we want to identify that defect. For example, if you're going to read OCR characters, however big your characters are, you want at least 30 pixels to see that height of that character or the width of that character. Or if you're going to do a defect, we want to have at least 3 pixels seeing that defect for the most, for the minimum amount of reliable way for your camera to actually be able to determine the defect. So we start off by calculating the minimum image resolution that we need, which is the smallest size defect divided by the pixels per defect. So if we want to do, a defect that is 10 or 1 millimeter long, and then the pixels per defect to be 3 pixels per that 1 millimeter, our resolution is 0.3. Our resolution power is 0.33. And then we take that image resolution and we say, okay, in 1 millimeter, we need 3 pixels. So if we have a whole field of view, which is this much, and we need 3 pixels per 1 millimeter, what does our resolution have to be? And that's where you take the field of view and divide it by your minimum image resolution. So that can actually get you your minimum required resolution to see the number of pixels per your smallest defect. Again, same formula as before. You can calculate your magnification by dividing the horizontal length of the image sensor by the field of view in the x direction. So an example to kind of make it a little bit easier of what I'm explaining, we have a situation where we're trying to read OCR code on a granola bar wrapper and then a barcode as well. The barcode is 1.5 inches tall and 1 inch wide, or 1.5 inches wide, 1 inch tall. Characters are 2 millimeters tall, and the part is going to be presented in the same direction. The field of view is about 153 millimeters as well. The line speed is 90 feet per minute, 460 millimeters per second. There are some constraints, but we don't need to worry about that right now. So to calculate the resolving power, we calculate our image resolution. So if our text is 2 millimeters tall and we need 30 pixels in that direction, our resolving power is 0.067 millimeters per pixel. If we throw that in to calculate our minimum image resolution, we do 153, our field of view, divided by our just calculated image resolution, and we get 2,284 pixels. That means in the x direction, we need at least 2,284 pixels to be able to get 30 pixels in a 2 millimeter distance. Obviously, there's not a camera that's 2,284, so we step up to the next closest one. So a 5 megapixel camera, which would be 2,592 pixels by 2,048. And we can confirm it in the y direction to make sure that that works as well. So 2,048 pixels times our image resolution is about 137 millimeters, so about 5 inches, which was plenty for a field of view in the y. So we know we need a 5 megapixel camera based on just our formula and what we want to see and how we want to see it. Now, as I said, we can go back and calculate our exposure time. So if our conveyor speed is about 460 millimeters a second, we can do 1 pixel, our blur, times our field of view, 153, divided by our speed in millimeters per second. We have to make sure our units are the same, and then multiply by our resolution in that direction. So we're at about 128 microseconds, which pretty much means we need to overdrive our light. But that's how you can calculate the required resolution and the exposure time of your system. And this is one thing to keep in mind. This is all the theory. You can calculate these things, but then when you actually go to set it up, it might not be exactly perfect. So maybe consider this as a jumping off point, your camera resolution, but your exposure time might change depending on the light that you choose, et cetera, et cetera. So This isn't a hard and fast rule, but it's a good way to get an idea of where you're at when you're getting started. So that's all we have for camera techniques, and camera considerations. Now we'll focus on lensing techniques and how to pick the correct lens. So we'll talk about the different kinds of lenses, CCTV versus macro versus telecentric, the focal length, what vignetting is, and then useful formulas on picking the correct focal length as well. So the types of lenses, there are CCTV lenses, which are fixed focal length. So the pro of these is the field of view and the working distance are adjustable. These are kind of your standard lenses when you think of machine vision, you know, your f/25, etc. The con of these is you can get some image distortion. Lenses are getting better, and lensing companies are always trying to come up with a lens that doesn't have a lot of distortion. But for certain inspections, such as measurement or high resolution, you want to factor that in. Distortion can be an issue. If you're trying to have the least amount of distortion, then you step over to a macro lens or a telecentric lens. A macro lens will have a fixed working distance. It'll have less distortion, but the downside is the working distance and the magnification are fixed. A telecentric lens will have a fixed working distance as well, but lower distortion. It's got a very high accuracy, but in order for a lens to be telecentric, it comes in a parallel direction, which I'll explain a little bit later. So the diameter of the lens has to be the size of your field of view. So it usually works only for smaller applications. That being said, there are telecentric lenses for very large field of view applications, but like I said, the diameter of your lens is the size of your field of view, so that can get very large and very costly very quickly. So a macro lens versus a telecentric lens. A macro lens is going to be a little bit brighter, and it does have a high resolving power, but it does have a shallow depth of field. And it works kind of the same as your standard, CCTV lens, where everything comes back to the fixed point of where your lens is. So if you're looking at an object that has different heights, you will be able to see the sides when looking at certain images. So whatever is in the middle will be flat, but as you get out to the edges, you'll be able to see down. So if you're trying to measure, for example, the pitch in this scenario, this is not going to be as accurate. A telecentric lens, on the other hand, is not as bright, I guess, but it does maintain a constant viewing angle because everything comes in significantly more parallel. So measuring the pitch, we get an image that looks like this. This is going to be a lot more accurate. So here's kind of the difference of how the light comes in for a conventional lens versus a telecentric. Here it's going to come in at an angle versus straight on. So this is why we're able to see down the edges of anything that's got height to it. But a telecentric lens, because it's made differently, comes in much more parallel. So here we're still looking straight down, even at the edge of the field of view. So now when we talk about focal length, that is the distance from the center of the lens to the point at which the light is focused by the lens. Different focal lengths will have different viewing angles. A long focal length will have a very narrow viewing angle, and a short focal length will have a much wider one. So these typically work well for smaller field of views, and these work well for larger field of views. It's important to consider the focal length when considering your application. It's not necessarily just, this is what my working distance requires. There are ways to pick a lens that will make your application easier, or picking the wrong lens will make it harder. In this example, we're looking at the top of these pins, and maybe we're inspecting for presence, absence of the pin, if it's broken or not. If we use a wide angle lens, an f/16, and a very short working distance, we're getting that wide field of view, so we're able to see down these edges, but we're looking straight at the top more in the middle. So if we're trying to see the presence, absence of something on the top of the pin, it'll be pretty easy here in the middle, but it gets harder as you move out to the edge of the field of view. Versus if we use a longer focal length, which has a more narrow emitting angle, we're able to look at the top of each one of these pins, even though this isn't necessarily a telecentric lens. That being said, our working distance is 200 millimeters, but our lens is 50 millimeter focal length. So here's a situation where picking the right lens would make this a lot easier than picking a shorter focal length. Sometimes it's the opposite. Sometimes we need a shorter focal length to solve our application. In this situation, we're looking for a defect on the inside of a bottle. Having a shorter focal length, we want to see down those edges. That's the point now. So now we can see those defects pretty clearly. versus with the longer focal length, we can't see those defects as well, and it would be a lot harder, arguably unsolvable for this application. So this is one of those situations where you want to consider, when you're building a machine especially, you always want to consider, if you plan on doing inspections with machine vision cameras and technology, what constraints you build in. Because if we had a constraint where our working distance had to be longer than 10 millimeters, we would be forced to use a longer focal length, and that would make this an application significantly harder, almost impossible. But if we knew we were going to do this inspection before we built the machine, we could factor in 10 millimeters of clearance over the part and make it easier down the line. There's reasons to factor in machine vision for lighting as well. We've talked about in other seminars, but there's just, it's important to consider lensing as well. When talking about our field of view and different focal lengths, if we keep our light working distance, or in this case our working distance, the same, but we swap out the focal length of the camera, how does that change our field of view? So when we have a really short focal length, 2.8 millimeters, we can see the whole city, we can see the person, we've got a very large field of view. But as we step up and get longer focal lengths, we get a smaller field of view and we get zoomed in more, so we can see less. So this is just an example of what different focal lengths will give you, keeping all other parameters exactly the same. So now we've seen this image before with our area scan camera sensor sizes, and I said it would work in well with lensing, and now I'm going to talk about why. So your sensor size has a certain format, 1 inch, 2/3, etc. You can Google the sensor, like I said, to figure out what that is. Well, lenses also have an image circle that will have the same format. So if you take the sensor size of your camera and then the image circle of your lens, which is letting all the light in to your sensor, you want the image circle to be as large as the sensor, so all of the sensor is getting light. If we pick an image circle that is, for example, 1/1.8 inches, that's too small. When we overlay them, only the color that is within my image circle is going to get light. All of these corners are not going to get any light, so they're going to appear dark. So you can see here, I have a small image circle and a larger sensor size, and you can see exactly where that image circle is in my picture. You can use the same size, it's perfect. You can even go larger, but it's not as good, but you can't go smaller. And sometimes it's very subtle. Sometimes it doesn't really seem like it's vignetting, and it seems like it might be a lighting issue, but it still might be. So if you ever see just kind of darkness in the corner that you can't really seem to get rid of, confirm your format of your lens to the format of your sensor. So now that we know what lens to pick, the format of it, what kind of lens, for the fixed focal length lenses only, not telecentric or macro lenses, because those are fixed, but if we're trying to figure out what focal length lens we want to pick, there's actually a formula that we can use. So the ratio of the field of view to your sensor size is the same ratio as the working distance to your focal length. So we can actually use that to calculate the focal length by multiplying the sensor size of our camera by the working distance divided by the field of view. So for example, if we have 50 millimeter field of view, 200 millimeter working distance, and we know our sensor size is 8.8 millimeters in the X direction, what focal length do we need? And it ends up being about 35.2 millimeters. So we need a 35 millimeter lens, but it's not going to be perfect. So we either keep our 35 millimeter lens and our working distance and have a slightly larger field of view, or we increase our working distance to about 233 millimeters and use a 35 millimeter lens. The other option is use a 25 millimeter lens with an extension ring, but that's not always great practice. You avoid extension rings if you can. They're great if they're necessary, but they can add some distortion to your image. So back to our example that we talked about before, where we calculated our required resolution and our exposure time. If we were going to calculate a lens for this, the machine constraint is 2 foot clearance above. So we have the field of view is 153. We know the working distance is 600 millimeters. It's, for example, the same sensor size as before, 8.8. The focal length is going to be around 35 millimeters as well. Again, we can adjust either the field of view or the light working distance to make it perfect, but it gets us a good place of what lens, what focal length to use. Some lenses will come with a lensing table to show off what their working distance and field of view will be. So if you want to use a lensing table like this, you have to know two of the three parameters. You have to know your working distance and your field of view, or you have to know the lens focal length you're going to use and your working distance to get your field of view, etc. So for example, if we have a 2/3 inch sensor size, we're going to look on this left here because this is data for 2/3 inch. This is data for 1 inch. So we look on here for 2/3 inch sensor size. Our field of view is 300 millimeters, and our working distance, is 300 millimeters, and our field of view is 175. We're looking at a green line, and this green line is a 16 millimeter lens. So again, we'll have to make a little bit of adjustments. Either the field of view can go down to 165 or increase our working distance to 330 millimeters or use some type of spacer. But if you see any lens tables, that's how you read those. Next with lenses, we talked about the f number or the aperture. I kind of touched on this at the beginning that there's a trade-off here that I'll get into, but what the f number is essentially is how open your aperture is. A smaller f number, f2.8, means it's open as far as it can, and then a larger number, f16, means it's as closed, means it's more closed. So f8 is half open, half closed type of thing. And when it's fully open, it's letting in all of that light, and when it's fully closed, it's blocking light. Or the more it's closed, the more light it blocks from entering. So kind of what I talked about in the beginning with considerations of depth of field and stuff. As the diameter of the aperture is decreased, the brightness and resolution change. So my brightness and resolution decreases, but my depth of field increase. So you can see I won't have as clear of an image, but all of these lines are in focus versus when I have a very open aperture, I have a lot more intensity and a crisper image, but I only have about, maybe 3 or 4 lines that are really in focus. So this is kind of where you find the happy balance for your application. How open is your aperture versus how much, how much height is there in your sample that you need more depth of field, that you trade off how open your aperture is. This also is factored into how intense your light is. If your light is bright enough for you to close your aperture to get more depth of field, or if you need a brighter light, or if it's not bright enough and you have to open up your aperture really wide, you're trading off there. So no situation's perfect. There's not one answer for every single application. It's going to depend on your applications as they come up, but these are just things to consider for each one. So your depth of field is decided by the f number we just talked about, the pixel pitch, the focal length, and the working distance. So for the f number, the darker the image or the larger number, the more your depth of field gets deeper. For the pixel size, the larger the size, the more depth of field you get. Your focal length, the wider angle, which is lower magnification, the deeper you get for depth of field. And then your working distance, the longer working distance gets you more depth of field as well. So if you're really trying to make your depth of field very long, you've got a lot of height to your sample, you can consider all of these factors to make it essentially as long as possible. So there are a lot of things to consider in terms of aberrations for lenses. CCS is a machine vision lighting company. I'm talking about cameras and lenses. That doesn't mean we're necessarily experts on them. If you have questions about either one of these, please talk to a camera or a lens distributor or manufacturer. The reason I bring this up is because I'm only going to touch on a few aberrations that can happen in lensing. And if you're looking at a lens, you're not really sure what to do, please reach out to a lensing manufacturer. They'll be able to talk you through a lot of these aberrations that can happen and help you pick the right lens to make sure you're getting the best image. But I'm only going to touch on a few of these. There's a lot more that can happen. If you want more information, again, reach out to a lens distributor to kind of talk you through all these. But the ones I am going to talk about are distortion. So distortion is where the image is distorted. So the shape of the object is altered. On a barrel distortion, the objects on the outside look smaller. On a pincushion, the objects on the outer edges look larger. So it just essentially changes how your image looks in the camera. Lenses are always trying to say, low distortion. They'll give a value, distortion of 0.5 or something along those lines. And that just means how much it can distort the image. So the lower, the better. That being said, Telecentric lenses usually have the least amount of distortion. Fixed focal length will have the most, but lensing companies are always working on creating lenses that have less distortion. The other distortion that comes up for us when we work with lighting is axial chromatic aberrations. And this is where different wavelengths have different refractive indices, so they focus at different points. You can see in this image here, when I turn a red light on, keeping every other factor the same, the 25 mark, maybe 26 are in focus and everything else is blurry. If I leave everything the same, turn off my red light and turn on my blue light, my focus switches from 25 to maybe 27, 28, 29. So this is a situation where if you're using just one color light, you just set your focus and everything's going to be fine. If you're using a full color light where you have maybe one sample uses red and then another sample comes in, you turn off your red light, turn on your blue light, your focus might be a little bit off, so you have to make sure you're doing certain things to make your depth of field larger. If you're using a white light, this can kind of come in handy too to know, because you'll have your red light will be in focus, but anything that's outside of that might be a little out of focus. So you'll get the best focus with one color light with optimizing your aperture, etc., to make your sharpest, most focused image. There are also extras that you can put on lenses. There's the lens itself. You can add a rear converter lens, which will increase the magnification without changing the working distance, or you can add an extension tube, which will reduce the working distance and increase the magnification. That being said, that's all I have today for cameras and lenses. Again, this is just the basics for you guys to get a good idea of how to get started in machine vision. If you have more questions, feel free to ask us. We're not camera or lensing manufacturers, so also feel free to ask any camera lensing manufacturer for more specific questions as well. But thank you for your time today. We'll take questions now.